So thanks everyone for joining us. Today we're going to be focusing on trackbed stabilisation, which is something that's quite unique for Van Al and a bit of a USP. So in today's presentation, we'll go through what trackbed stabilisation is, the subgrade problem as we call it, and the development of the TBS system and how it came into being, the design approach that we use, the installation methodology. We'll then run through a couple of case studies to explain where it's been used. We'll then have a look at one of the more recent developments, which is vision-based monitoring, and then design and optimization through finite element analysis, or FEA as we call it for short, and then questions and answers at the end. So the problem with trackbed or trackbed stabilization and the need for it is to correct poor track geometry due to subgrade failure. So we rely on the subgrade to support the rail system. So the loads that are being put through rails and sleepers and ballast bear on the substructure below, the subgrade as we call it. And in certain instances, and for a variety of reasons, we can end up in a situation where that subgrade fails or begins to fail, either through cyclic loading, where we can see sort of critical velocity failures that we'll explain more about that. A lot of it can be affected through water or moisture conditions, and as a result of that, we see increased maintenance costs, the need for temporary speed restrictions, the reduced utilisation of track, and also potentially reduced line speed as well. One of the main and regular observations that you'll get from a trackbed site is something that we call cyclic top, that I'm sure you're all probably aware of. It's detailed within Network Rail standards as well. And that's effectively where we start to get a wave that propagates due to poor subgrade. And in some cases, it can actually be serious enough to result in a derailment. So where did TBS come from and the journey so far? So Van Al were first involved in around 2015, where we're engaged by Network Rail through their innovations team to look at a system to be able to deal with poor subgrade, but at the same time leaving the track in situ. So we developed ideas around this. We went through a research and development phase and proof of concept, to which we were successfully pointed on to the CP5 trackbed stabilisation framework. And we continued development of that system and proof of concept with Network Rail. We developed an installation system, which is the Spirit Mast, as we call it, that I'll explain more about shortly. And then went on to full-scale trials undertaken at Brind Phase 1. We then extended that scheme due to the success there into Brind Phase 2, and then assisted with a guide to trackbed micro-pilot. We then went through project delivery at Ashton Moss, Kintbury, Barking Riverside, Kirkconnell. We did a pilot project for Irish Rail. That's one of our case studies that we'll talk about today. We then secured Innovate UK funding for a KTP, or Knowledge Transfer Partnership project with Nottingham Trent University, and then went on to do Kentish Town Transition Slab Track, Kintbury Phase 2, and Muston Cottage was the latest scheme that we've completed. So a real variety of different schemes over the past few years. The design approach that we take is improving the track stiffness by improving the subgrade. So smart piles, as we call them, are installed to target the areas of soft or variable subgrade. They're installed through the track, and it's a track-in solution. So that maximises possession time, minimises disruption. There's no curing time or wet works. And the pile cap is set 500 to 800 millimeters below the underside of the sleeper. And that allows for continued maintenance and tamping and high output renewals. So it doesn't affect ongoing maintenance. If we to look at the design approach with the ground conditions removed, what you can see is a bank or a series of screw piles with a lead section at the bottom of the pile that we use to bed into firm material. There's then a series of extensions that we can vary to increase the length of the pile as required, and then a cap that shares the load to the underside of the ballast layer and transfers that load back up through the track system. If we to put that into finite element analysis, you can see there that the heat map basically shows the load transfer from the rail through the sleepers, through the ballast, through the pile cap, and then down to the more competent, strong material at depth. So effectively, it's creating a vertical bridge between the ballast through the weak soil down to this stronger, more competent soil. The other concept that we rely on within track bed stabilisation, and as a result of leaving the track in, is that we need to get the ballast to work in a form called soil arching or bridging. So what we do is we install the piles between the sleepers. We need then to transfer this load from the top of the pile through to the underside of sleeper, and we do that through using the rail ballast that's already there. There's more details on the design approach in A Guide to Trackbed Micropiling by Peter Musgrave, Mohammed Webby, etc. The other thing to note as well, and I've seen Adrian Staples has joined the call, is we went through quite an extensive period of product acceptance to get this PA'd for Network Rail. Obviously, it's an item of plant, designed and built in-house, so it's an exclusive system to ourselves, built specifically for this purpose. So we need to be able to install screw piles at high tolerance in a safe manner, so it's fully guarded and interlocked. There are a lot of safety and control features on this mast over and above what we'd see with normal screw piling attachments, something that we're quite proud of. So to put it all in perspective how it works, one of the case studies we've chosen is Coracle in Bog, which is a pilot project we did with Irish Rail a couple of years back, and it was on a section of track not far from Athlone and sits directly on the Dublin to Galway line. The main challenge for Irish Rail is that Dublin to Galway travel times by train is longer than it is by car, so there's no real incentive to catch the train, and that was generally driven by track stiffness. So the controlling factor for line speed was that the track stiffness wasn't sufficient to increase speed. So by improving track stiffness, you can increase the line speed and reduce CO2 emissions. Ireland, for those that aren't aware, is one of the main areas of bog formation in Europe. So if you were to look at all the areas of bog, raised or blanket bog, the two different formation types are highlighted on the map. And when you superimpose the Irish Rail network, you can see that the middle section of the country, pretty much most of it crosses a bog at some point in time. Back when the railways were constructed, they obviously tried to avoid peat bogs as much as they could, but unfortunately it just became impossible to do that. So at some point, the railway needed to cross over the bogs, and that's generally where the issues come from. So the site chosen was on the Athlone branch, approximately 4-metre embankment throughout the section. We planned a 100-metre long trial area, pretty much central between Dublin and Galway. You can see from the aerial photograph there as well that some of the bogs still remain worked, so they're used for material that's then recovered from the bogs for heating. So from an identification of a problem perspective, obviously the first thing that we rely on is maintenance tamping records, so that you can see from this with the time up the side, from July 2012 to August 2018, there were repetitive tamping cycles, and a lot of this based on seasonal moisture variation within the peat. So as the seasonal moisture levels varied, you'd see rapid settling of the peat, which would then result in additional maintenance in the form of ballast drops and tamping. So this is a good identifier that there's a problem, and it also starts to thin down the areas to where we need to target as well. To look at the sites themselves, and this is pretty common across a lot of the trackbed sites, there's nothing that stands out immediately as being a massive problem. It's only when you start to look at the actual data it starts to stand out. And you can see front and rear cab footage from the train doesn't really show anything. So the first thing we do before any project is a desk study exercise. So we look at drift geology, we look at existing ground investigation, and we start to scope out the limits of any issues. One of the really interesting things with this project was that we were actually gifted with ground penetrating radar data, thanks to the guys at Irish Rail. So if you look at the top 3 plots, what we can actually see is a red dotted line, if you can zoom in enough to see that, which is a theoretical ballast thickness. And what we can see towards the right-hand side of the trace is that the actual ballast thickness increases massively. So we go from, rather than having sort of between 500 and 600 millimeters of ballast, we've got in excess of a metre of ballast. And what that is showing is basically those successive ballast drops and tamping regimes have basically forced that ballast to propagate down into this softer material. That's ballast is being effectively lost into the bog. So from that, what we could then do is use traditional ground investigation in the form of window sampling to go and target the location. And what we found, looking at the resistance plot from the dynamic probe on the right-hand side, is that you can see a sort of 3-meter railway embankment with a peat layer where we've got very little resistance, and then we start to gain resistance as we hit the sand and gravel layer. So from a pile design perspective, we can use that to start working up a very basic design. All the ground investigation findings are then plotted, and we develop what we call a ground model, so where we can see the ballast and the track construction, peat layers, soft clay, the sands and gravels at depth, and then eventually a competent limestone. So once we've got a target pile length in mind, what we then do is go and install a test pile, and we use a PDA, pile driver analyzer, which actually gives us an inferred working load for that pile, so we can go and prove it in situ. And that gives us a resistance plot for the working load of the pile. The other element that we needed to check, obviously this peat layer being sort of circa 4 meters thick, was thicker than anything we'd encountered in the UK at the time. So we undertook a buckling analysis as well to make sure that because of this lack of restraint around the center section of the pile and the potential to induce a kink or a buckle, then we needed to account for that within the design parameters as well. So at that point, we could then start to develop a design, and you can now see we've got piles every sleeper crib between the sleepers each side of the rail, working in pairs all the way through that section and varying in length to match the more competent material depth. We then also, for verification purposes, undertook some void monitoring. So on the 100-meter section, we applied void monitors, which I'm sure a lot are probably aware of these. So we use digital void monitors to measure the voiding, which can give us a comparator to compare the track bed performance. So pile installation, piles are normally delivered to site in stillages, as you can see. So they're prefabricated sections with bolted connections, which is one of the strengths of the system, is that we can vary the pile lengths as we see fit or need to on site to account for differing ground conditions as we go through the project. From a logistics point of view, it's very efficient as well. So it means that we can store lots of piles on the stillages ready to go. And bolted connections are very simple and easy to prove from a design perspective and are quick to install. So this is the typical example of where you see the spirit mast on a road railer, a second RRV with a trailer that'll be effectively running as the logistics RRV, loading the materials out to the installation team. So this should show a short video taken up on Brind on phase 1, just the actual installation process itself and the simplicity of it. And you'll note as the piles are installed, there's very little ballast disturbance at the sleeper end as well, which is one of the main strengths with the system, is that allows us to work in restricted possession times and be able to hand back with minimum checks, minimum amount of tamping and can go back in, etc., to make the track safe for hand back. So post-installation monitoring. So using the void meters, we found that if you look on the data, there's 2 vertical red lines. So pre-pile installation to the left, while we were doing the pile install through the center, so there's some disturbance to the void monitors, and then post-pile installation afterward. So on this particular site, we saw an immediate 50%-ish reduction in track deflection using that void metering data. And for those that are interested, there's actually a write-up in the 2020 edition for the July 2020 New Civil Engineer. Another project that's quite interesting in itself is Kirkconnell Embankment. So this was up on the Glasgow lines, 250 piles that we installed up to 8.5 meters long. This particular site had a couple of issues. One was track settlement, but the second was that it was sited on what we suspected was a rotational landslip. So you can see from the pictures there, the site itself, where the red line indicates, is just above what is quite a steep embankment that was being undermined by the river. Everything to the left-hand side of the photographs, the northern end of the site, was at one point an open cast mine, and over time, as the open cast mine had been decommissioned, water levels had rebounded to their natural state and increased the instability in this slope that was already probably on the edge of a failure. So solutions were looked at. Our client QTS got us on board, so they were looking at doing a track out solution. So remove the two existing lines, the up and the down, excavate out the affected material, and reinstate that embankment with an engineered fill. However, it became apparent that the 10-day blockade that was planned to undertake these works wasn't going to be sufficient. There were also other issues that were thrown into the mix during the planning stage as well, insofar as otters on the lower embankment, and also the amount of road traffic that we'd need to get sort of 10,000 tons of material in and out of the site as well. So there was a different solution needed. So we started to look at this with the potential to use it for a trackbed site. Boreholes had already been undertaken, and we could see that there were different fill layers for the embankment. We'd also got very variable bedrock levels and alluvial material cutting in at mid-depth as well. So from a piling perspective, it was quite a challenge. The detailed design that was done by the Network Rail team in Birmingham came up with a pile design that would then work for the project. Then we then deployed to site. So it's the same equipment again, this time working with two teams. So one team on the up, one team on the down. The job was completed without any safety or quality issues in 8 shifts. So we managed to win 2 shifts back on the program, reduced the amount of material off-site, and avoided large import of quarried stone. There's less disturbance to the otters on the lower slope, less HGV movements, which on local country roads is a massive win. No requirement for third-party land access, so that saved time and hassle. And no removal of the P-way, so other works were allowed to utilise the blockade with engineering trains, which meant the other works within that blockade could be delivered more efficiently. One of the later projects that we've done is Caversham Road Tunnel down at Kentish Town. So this was looking at using this technology on a section where they were removing slab track. So the limits of the slab track outside the tunnel were to be removed and reinstated with normal ballasted track. But this meant that there was a transition zone on and off the existing slab track that was going to remain in the tunnel. So working with Amy, we came up with a solution to develop a precast element that would be installed at the tunnel mouth that we'd then screw pile and fix in place. And this would provide a run-on, run-off slab. The pile design was tweaked slightly so that the pile cap was adapted from having the double flights on the smart cap that we saw earlier to this solution where we've got a set of shear studs that can then be used to grout into the precast concrete element. And that all fits together, as you can see from the computer simulation there at the mouth of the tunnel. And then this was the physical install over the Christmas blockade. Long-term case study that we always kind of reference back to is Brind Phase 1. So this is the first project that we did for Network Rail, and similar to RX Rail example, nothing that stands out as being a major problem. Although when you look at the track, you can see there is a slight cant on the track that shouldn't be there, mainly due to the embankment starting to move and fail. There were historic track quality problems as well. And a lot of the monitoring had been done by NMT, so New Measurement Train. The advantage with this is we keep getting these data plots, and we can see that from sort of January 1996 all the way through to when we did the pile install of summer of 2018, there have been various different maintenance interventions in the form of tamping that had corrected the track geometry. However, after the installation in summer 2018, that track attrition rate and the constant tamping that had been ongoing had reduced massively. So that indicates that that was a successful system. And we can see that from the actual figures from a track deflection perspective as well. So the next step that we've been working with is looking at some of the data associated with this system. So we've been looking at working with Nottingham Trent University and Innovate UK as part of a knowledge transfer partnership to develop vision-based systems. So Kuyar Faizi has been working with us as our research associate to develop a vision-based monitoring system. So the VB technique uses image acquisition, so a camera in this particular instance, that's modified for site use, and then video processing. So that's basically a computer program with software that filters a signal, applies an algorithm that we developed, and the output from that is displacement measurement over time. So we can see there a void meter on the left-hand side. We've also then got a bank of targets and the typical displacement measurements that we'd look to see. If we run that in a live scenario, it runs for a little while before we start to get any actual figures. But you'll see in a moment on the left-hand frame on the video that you'll start to see the vehicle, the train in this instance, start to pass over the sleepers, and what we'll start to get is real-time displacement data from one of those targets that you can see. But the advantage with this system is that we can monitor multiple targets at the same time. Whereas traditional systems, you're either taking fixed measurement or measuring a single target. With this, we can measure a bank at the same time. So what we can also look at is displacement and movement between the rail and the sleeper, which would indicate whether clips and pads are working correctly. We can also monitor different elements or reference targets as well. So it's a really successful system that we've managed to develop thanks to QER's hard work. Using that in real life, this is one of the example schemes where we've been piloting this as a system. And you can see also that we can use different train classes and types to be able to make a different assessment on speed and loading as well, which obviously vary the trackbed design. And the real advantage with vision-based management is that it can be used to calibrate the FE models. So finite element computer programs are what we use with other tools. And we basically generate a numerical simulation of the track, and we can monitor its response as we actually impose loads on that. So you can see there are two different examples of how a non-piled and a piled trackbed would respond to with displacement indicated there. And we can use our vision-based system to calibrate the model against real life. So looking at the heat map there, we can see in the top an illustration before piling, and then using the same parameters after piling, that those displacements have been passed down into that stronger stiff material at depth and reduce the overall deflection that we're seeing at track level. What we can also start to look at as well through an optimized design package is we start to look at critical speed and critical velocity. So this is basically when the rail displacement reaches its maximum value. So you can see there on the left-hand side, we can map out train speed versus maximum vertical displacement and get to a point where we can establish this critical velocity, which you can see on the charts on the right-hand side, how critical velocity starts to look when we start to introduce Rayleigh waves and various other factors. And what we can also do within this is use this as an optimization method as well. So by using FEA, what we can do is plot the displacement. We can then look at different pile arrangements and then look at that from a cost benefit perspective. So there's 4 examples there where we've got different pile layouts, different reduction in track deflection, so 42%, 51%, 30 or 39% respectively, versus the cost as well. So to sum up, the advantages of EBM used in trackbed monitoring are, it's a non-contact measurement system, so you need less access to the rail, so it's higher from a safety perspective. It's high accuracy in measurement, so it's sub-millimeter, it's cost effective, can be used to measure void. It can also be used to measure lateral deflection, and it can be used to calibrate our finite element models. And obviously on the back of that, the finite element approach can also be used to establish vertical deflections and obtain an optimum design for trackbed stabilisation. So that's it from me. Thank you for listening. Are there any questions?
Okay, well, it's open to the floor now. If anybody's got any questions or in the chat box, please, this is the chance to speak to John, the expert on this subject. And I'm sure you've probably come across this in other places out there. So you should have experienced where you work and whether you've seen anything like this. Has anybody seen this type of work being taking place on their area? Nobody got any problems out there? We have a get. Jay Beckett, do you want to ask a question?
Hi, John. Yeah.
Yeah.
You were mentioning that after the piling takes place, what kind of sort of afterworks have to be carried out? So, in terms of tamping or packing, what exactly needs to be done after the piles have been installed?
Oh, yeah. Yeah. So it generally varies on the condition of the track that we're left with from the start. So if you can imagine, a lot of these sites exhibit signs of sort of wet bedding, or you might get sort of material propagation into the ballast. So it really depends on quite how bad that is. So sometimes we'll go in and pile in advance of a relay or a renewal. Other times that's been done first. So in general terms, we usually insist that the track's tamped before we go in and corrected geometry wise. We'll then look at ensuring that the ballast is topped up to level. Once we've done the piling, we'll then go through and either can go at the end of each shift and then tamp at the end of the full installation, depending whether we're working midweek nights or on a blockade, etc. And that'll also dictate the level of track monitoring that we need as well.
Okay, great. And what kind of time frame would the piling take, sort of per, I don't know, length of track?
Yeah, I mean it varies on obviously the pile length, the material we're going through, and the depth of ballast as well, because getting through the ballast can sometimes be a bit of a challenge. But yeah, in general terms, we normally work on 15 to 20-ish minutes a pile, to put it in perspective. So yeah, within a midweek night 5-hour possession, you can achieve what is quite a reasonable output for short possession windows.
Brilliant. Yeah, great. Thank you.
Good question, Jay. We've got a question, John, from excuse me, my pronunciation, Cresmian. Would you like to go next?
Yeah, hello, hi there. Yeah, it's Matt from Bar for BT Rail. Yeah, I just wanted to find out. It's a fascinating story with the all the piling and the truck stabilization. So, because I've noticed your piles are galvanized steel. So, what sort of lifespan they have, and then is there some sort of maintenance required with them?
Yeah, so there's no maintenance requirement. They're designed at 120-year design life. So we allow for loss of section on the steel tube in the flights, which is accounted for through the usual way through Eurocode 7. So we allow loss of section for that, but we also galvanize as a belt and braces approach. And that's mainly because the center of the pile, in some instances, can have oxygen present, because obviously as you install the pile, there is the potential that displaces the soil from the center stem to depth, so you can end up with a void. So yeah, the galvanizing really is more for inside the center of the pile, and in some instances we've actually grouted that as well, where we suspect there to be quite aggressive ground conditions and things. But yeah, so hopefully that answers your question.
Thanks for that one.
Just one more.
Oh, sorry, yeah, no, carry on, Matt.
Yeah, just one more, because obviously it comes in a section, so obviously your weakest link will be on the bolts. Will this 120 as well apply to the bolts?
It does, yeah. So they're a spigot and socket connection. So in theory, they do work without the bolts actually physically being installed as well, but we apply the same test to the bolts as well. Yeah.
Thank you.
Okay, okay. Daniel Teese, you've got your hand up there.
Hi, John.
Hiya.
Just a couple from me. We've got the similar site at what you had where you had the old mine under it. We've got a similar site in Manchester there. If we were doing that, would we have to get the geometry right first before we put the piles in, or can the piles be put in and then we get the geometry back to the place where we want it after the piles have gone in?
Yeah, it's a good question, actually. Yeah, so in theory, either way round works. The reason we always prefer to correct the geometry first is it gives us a position that's fixed, so we know where the track's theoretically going to end up. And it just makes life easier from a setting out and levels perspective. Obviously, the level of the cap needs to be set quite accurately against the sleeper level, so it just speeds the process up if the track's in the correct position before we start. However, you know, it's not impossible. We did a job at Ashton Moss a few years back where we had to basically had to establish every single pile position independently, because all of the track positions were going to change as they did a renewal and plane line a set of points and various other things. So yeah, either way around is entirely doable.
And the second one is, how successful is it through S&C?
It's a good question. In theory you can, but we've never done it. It's something that we've looked at before. We are actually looking at a project over in Canada where we're looking at exactly that. That's something that they're interested in. Obviously, tolerance on S&C relies more on everything being fixed and set. So yeah, I think there is an application for S&C, but we've not done it in the UK yet. So it might be a first.
Right. Could you come and see me at Stockport?
Yeah, absolutely. Yeah, grab me details. We'll pop up. That's not a problem.
Yeah, I'll put my email address on the chat.
Brilliant. Yeah, we'll be in touch.
Thanks, John.
Thank you.
John, just following up on that one, how sensitive is the track to the position of the pile then, if afterwards people move the track?
We're working it on a basis, like I explained earlier, about this ballast arching. So theoretically, we're almost doing a ground improvement method rather than a bearing pile.
Right.
So moving the sleepers around doesn't really actually have that much bearing on what the actual working load of the piles is. It's almost like you're doing a reinforcing blanket effectively. So wherever
like
you move the sleepers, yes, that's it. Yeah, exactly. Because you rely on this ballast arching to actually transfer the load.
Yep. Yeah, I remember now. Sorry, I didn't pick that up at the time.
That's right.
Benjamin Ossibor, do you want to speak? You've got a question for John.
Yes, I do. Thanks. It's basically, I think Brian and Dan pretty much asked the same questions, but I just wanted to go into it a bit more. A lot of the times in a lot of renewals, the preference would usually be to do the piling work first, to get that out of the way and then get the renewal core done. Have you come across situations where you reach refusal, for example, and then you now have to do adjustments to the pile, for example, to make sure it's at the right level?
Yes.
And what would the protocol be for that?
Yeah, so when we do the pile design, we calculate an installation torque. So in the US, there's a big thing about they basically don't really design screw piles. They just install to a torque, which has never really been adopted in the UK, and for good reason. However, it has got its place. So we design the working load of the pile properly in accordance with Eurocode 7. But what we can do is calibrate that against an installation torque. So if we're on site, for example, like you say, and we hit early refusal, we can track that against the ground investigation through our engineering team and see whether that's something that was anticipated or not. Likewise, if we go through discrete areas of the project and we're finding that those installation torques aren't quite as high as they should be, what we can then do is take a view on whether we extend the pile as well. So it works both ways. And obviously, there's telemetry on the rig that gives us an accurate readout of that as well.
Okay.
It gets flagged through the on-call system, and then we'll make a decision with the designers as to what we do. So there's no cancelled shifts and hanging about. There is quite a clear sort of escalation process for if we need to do that.
Okay, so then two more. One, the first one is installation tolerances then. So how do you allow for what will be a reasonable tolerance to cater for the current renewal and potential maintenance in future, in terms of where that pile, like you rightly said, it's ground improvement rather than bearing. So where it ends up in the ground compared to where the sleeper bottom will be, how do you work that out in essence?
It depends on, so what we need to look at is your existing track position and what your planned track position is for your relay, whether you're going to do a track lift or lower. So that will obviously then drive the level that the piles are installed to and the position. What we then do is we have a physical measure that we use a drive bar to drive the last section of the pile. We will mark up what that embedment needs to be on that drive bar, and the engineer on site will then check against that every time.
Okay.
So that's how we control that vertical tolerance.
And then the final one, then looking into the future. So we do the pile installation, we put what we consider to be reasonable tolerances, but then there's a future renewal of that track for whatever reason. what is the risk of your sleeper, say, ending up underneath one of the piles and then creating a direct contact situation? Because it just feels like that's one of those things we wouldn't be able to control.
Yeah, we've
How do
modelled
we
that.
mitigate against that?
Yeah, we've modelled that previously. Obviously, with the pile head being set down below the bottom ballast layer, it has a minimal impact on where the actual sleeper is relative to it. On one particular project, the works delivery team there actually took to move the sleepers to see if it made any difference, which it didn't. So we'd installed that one previously. They displaced some of the sleepers over the top of the piles, and it didn't actually make any difference either. So we've kind of proven that in real terms. And it's all to do, as I say, with that ballast arching effect. But the other thing that you can look at as well is obviously things like using geocells when you go through and do your renewal. So using a geocell within the bottom ballast or within the bottom layer of your formation actually helps that bridging as well between the pile caps. So
Yeah,
that's
agreed.
another slightly composite design that you could look at as well. And potentially, if you're looking at doing that, you can also reduce the number of the piles as well.
Okay, I think that works, but obviously the issue with that will be with geocells. You look at your renewal time, and you would normally need to fill that in with sand, and then that just becomes an even different problem. But anyway, thanks.
Yes, yeah, exactly. Yeah, it swings and roundabouts. You're right, absolutely.
Yeah, but the person who gets it back at the end, the maintainer, would be more than happy, I'm sure, to see it put in, both those tolerance, if he's going to get some long free time for his track. That's good.
Yeah,
that's good. Have we got any other questions that somebody would like to ask John? Any experience that people have seen that in their areas where perhaps it might be useful to them? Yeah, Luke.
Hi Brian, hi John. Thanks for the presentation, Brian. I think we met last week on the PWI course. Yeah, it was only just to add to the previous speaker, just to say, obviously there's our products as an alternative to geocells. And I think I met one of your colleagues, John, last week, who mentioned he took one of my cards and was certainly interested in looking at how the two technologies can be combined. So certainly I can drop my email if you'd like into the chat, and then if you drop me an email, it would be delighted to look into that and how our ballast or sub-ballast stabilisation dual grids can actually address the challenges that people experience with filling of geocells and that sort of thing. So I'll drop my. It was just to add that, to be honest.
No, that's good. That's good, Luke. Thanks for that. Thanks for that. Because as you say, there can be a combination of problems that need to be sorted, and there's different ways of doing it. So that's great to get that input there. Yeah,
absolutely, brilliant.
Any other questions to add to that? Anybody want to take this opportunity? One of the pictures. Sorry, we've got one there. Was that one?
Yes, me here. Yeah.
Yes, please.
Just wanted to find out. Have you used it on the third reel, or fourth reel?
Yeah, no, we've not had the opportunity yet. In all fairness, there's a couple of schemes we've looked at and sort of scoped in the past, but no, we've not as yet. So that might be another first.
Do you reckon it might pose some sort of like issues in terms of conducting?
There is potentially, although it's a similar challenge to permafrost. So the next iteration and the next update to this will possibly involve using different materials that aren't steel. But I'm not going to say any more yet before I trip myself up. But yeah, we are looking at other things as well.
Agreed. Right. Cool. Cheers.
Good question. Very good. Yeah. I mean, you could be the first. Lee, would you like to ask a question?
Yes. Thanks very much for the presentation. It's very impressive. I have a question. When you install the piles, do you consider like the stiffness difference like along the track? So that means the pile should be different based on the actual stiffness of the track. Yeah, that's a very good question, actually. So one of the examples that we gave there at Kirkconnell was a key example of that. So across that project, I don't think there were two piles that were the same length. It was literally, up and down and all over the place, purely because of the variable rockhead and different material that we're encountering. So you're absolutely right. Some projects are quite easy.
Ground conditions are quite simple across the pitch. Other projects you can end up with vastly varying pile lengths, and I think that just goes to emphasise the importance of that desktop study and making sure that when you scope the ground investigation, you make sure that you recover the right information so that you're forewarned before you actually start the design based on something that might not be 100% correct. So, yeah.
Okay, thanks.
Thank you.
Any other questions that people want to ask? When you do you actually do any of the sites that have got wet beds then, John? I mean, what can you do for those sites? Isn't that or generally attrition, or is that down to ground conditions and support and strength? I don't know.
It depends, but it's generally down to ground conditions. So it's where you're looking at a cyclic failure of a clay or a fine material that then starting to propagate its way back through.
Yeah.
So by piling those locations, you can stop that propagation of that material. But obviously, the problem with that is to get the ballast arching to work is you need to do a ballast renewal as well as the piling.
Yeah. Yeah.
One without the other won't really necessarily give a benefit. So
right, and then protect the interface between the ballast and the formation as well, presumably.
Yeah, absolutely.
Yeah. So there's quite a lot of preparation work and desktop work that needs to go ahead before those types of jobs, isn't there?
There is. Yes, exactly. Yeah. That's
good. That's good. Any maintainers on here who want to ask a question about whether your area being used, or suggesting problems that you've got in your area, perhaps? No. Okay. Just let's bring it to a close then. If there's no more questions for John now, I'm sure John will be more than happy to answer any other questions that you think of afterwards, because often when we go away from these, we think, gosh, I wish I had asked that question, or whether you may not particularly want to ask it in front of everybody else, but certainly I'm sure you would take any questions afterwards, John.
Yes, absolutely. No issue whatsoever, Brian. Yeah, that's no problem.
That's brilliant. I was one thing that did intrigue me, I'll be honest with you. When you showed those pictures where you couldn't see any problems at all, who spotted there was a problem in the first place?
It all comes back from test train data. So
Right.
on NMT data, you can start to spot some of these sites, and that was where our vision-based system was developed from. Is when you're looking at NMT data, 1/8 and 1/16 of a mile is quite a long stretch when you're starting to scope out trackbed problems.
Yeah.
So you almost need to use your NMT data and then use a vision-based system to then dial in the limits of where the problem is.
Right. We brought on another question, John. I hope you're all right for a bit. Benjamin,
that's fine.
Benjamin Ozzybo again.
Sorry, it's just a quick one. Will the presentation available to be shared?
Yes, it is. Yes, that's been agreed. So yeah, there should be a PDF version that will be put up for everyone as well. So yeah.
No problem. Thank you.
That's great.
Sorry, just a quick one. The trouble with the presentation being shared is I think it's being shared on the PWI website, no, PWI shared drive. So most people can't access it until it's being put on the Knowledge Hub. So don't know how else people can access it before it's put on the Knowledge Hub. That's one of the problems I've encountered lately.
Okay. Yeah. I don't know how quick it appears on the Knowledge Hub. I thought it was quite quick, actually. I'll get that
up this afternoon, Brian. I've got a few to do, so.
Oh, that's great. There you go. There you go. Very good question with a very quick answer. How about that? There we go. That's great. John, that's been a great talk. It really has. It's you're obviously a passionate person. You're very professional in your approach there and the way you look at it. And it's great to see that you actually gather the information beforehand, don't rush into it, and prepare and do all the desktop stuff so that what is actually found is then put into the plan to finish it off. And what a variety of sites you've shown us, from Ireland to Kentish Town and to was it Muston Cottage in Filey? Brilliant, so it just shows you. And you know, I'm sure you're available to give advice to anybody who's out there who wants to get that advice.
Yes, absolutely. Yep, no problem.
Unfortunately, we can't all stand up and give you a clap, which probably could, but it causes problems. So I'm sure everybody will give a clap or put thumbs up in the site. And thank you very much, John. And thanks for everybody asking questions. And look forward to the next meeting.
That's brilliant. Thanks, everyone.